But on the other hand, it's this is algebraizable if I can find a algebra function h such that the solution to this first order differential equation in the algebra produces paths which solve this according to this rule. That shouldn't be f. This should be r of t in my language at the moment. So that's what algebraizable means, that you can take your integral equation for the vector field and swap it out for a first order differential equation in the algebra for the appropriate algebra, and then you can track back. After solving the algebra equation, you can find the integral curve for the original vector field, or correspondingly the system of autonomous differential equations. All right? So this proposition 2.1 is like the fundamental linchpin to the paper. It says that when can you do that? Well, you can do that. F is algebraizable. It's possible to find an H to make this correspondence happen, provided that there exists this pair of traceless matrices, which are, they're traceless, right? They have trace 0, and they're both perpendicular to the Jacobian in the sense of the Euclidean geometry of the 2 by 2 matrix space. So, I mean, to me, this is kind of surprising. I'm like, where's this coming from? I still don't have an intuition for why this should be true, but I start to understand his proofs of things. Except that I don't understand his proof of proposition 2.1 just yet, which is what I want to try to understand with you guys here today. Because what's his proof of proposition 2.1? Proof. What does it say? It says, now if I can get past this point, I think I understand the calculations that follow on pages like 5 and 6 of this. Basically, he takes an arbitrary 2 by 2 matrix, pair of 2 by 2 matrices. He gives them a 2 by 4 matrix, and then he describes different row operations that will inevitably go to three different possible cases. Those three different possible cases give you three different possible classes of algebras, each of which corresponds to algebraizable F. Now, I personally think, and he doesn't come out and say this, but I'm relatively certain that case 3 is the hyperbolic case. Case 1 is the complex case. And if I had to wager, I would say that the middle case includes the case that your vector field corresponds to a null algebra. But I'm just I mean, this is the basis of fuzzy speculation at the moment. Yes, and that's a good reason. Like you said, there was only up to isomorphism, three isomorphic classes of algebra over the real, so what I'm saying is inevitable. The question is which is which. Yeah. Oh yeah, explicit condition. Oh yeah. But here's the part I'm stuck on. Well, I'm not stuck, I just don't know yet. He says the proof is direct. It's direct of the corollary of the theorem 2 in 21. So, all right, what's 21? What is 21? Giving you guys a real research experience today, right? Not many undergraduates get to read papers and try to digest them. You know, this is actual honest-to-goodness math research. It's not like a fun textbook with all its cush definitions and preordained homework problems with their nice, well-defined edges, unless I write them. So this is, in which case they might not even make sense, but anyway. J. Ward, and this is his From Generalized Cauchy-Riemann Equations to Linear Algebra. Proceedings of the American Mathematical Society, Volume 4, Number 3, 1953. That is the last paper that I gave you guys. So let's see if we can make head nor tail of this claim. What is his theorem 2? It's at the end. That's the last paper. what I gave you guys here is the first paper is basically Ward's thesis, 1940 thesis. The middle paper is Wagner's 1940. I believe the middle paper is what? Wait, oh, I already put them out of order. Sorry. Doesn't concern you guys, but the middle paper is the 1948 or so, 1947 doctoral thesis of Wagner. These are both students, PhD students at the University of Wisconsin, who had their advisor was McDuffie. McDuffie, again, I think I told you guys this before, but he wrote a very popular linear algebra text of that time period. He's a pretty well-known guy. So their way of doing things makes sense if you look at McDuffie's book. Like McDuffie's book is very much the same style as these theses. All right, anyway, so what is theorem 2? You guys find it? What page is it? 460. All right. This probably requires us to read the whole stupid paper, doesn't it? I mean, I really don't, don't listen to me. I'm not saying this paper is stupid. In fact, this paper is precious and it's really kind of neat. Theorem 2, suppose the differential equation 17 has the property for some fixed integer p, it implies the set 18. What is 17? Trying to read these paper about make you blind. Let's see here. This is the sum. So here's my 17. Sum I and j equals to, I don't know, sum ij, and then d, kij, partial yi, partial xj equal to 0. And that's for k equals to 1, 2, all the way on to n squared minus n. So we've got these, well, that's the right counting to start with. We're given a set of n squared minus n first-order partial differential equations relating the derivatives of the dependent variable y's with respect to the independent variables x's. So this has the right kind of counting to be a set of Cauchy-Riemann equations. Right? Cauchy-Riemann equations, there's n squared minus n of them for an n-dimensional algebra. Right? So if you're going to, the whole point of this paper is to say, given this set of differential equations, I can create a corresponding algebra which picks these up as its Cauchy-Riemann, general Cauchy-Riemann equations. That's the point of this paper. But why that has anything to do with proposition 2.1, I don't know just yet. Let's try to, maybe we can discover it together here. There's still time, still hope. Keep hope alive. Let's see here. Where was 18? Oh, 18. This is 17, right? What's 18? 18. Oh. Oh. What's he doing? What's 18 about? You see these parentheses around that partial? You know what that means, probably? Do you guys know what that means? When he writes this? What are these suspicious big parentheses that don't seem necessary? What's that? And what's that sum over? Is that a sum over t? You think so? All right, I'll trust you guys. I hope you're right. T equals 1 to n of a sub t s r. My eyesight gets any worse. I'm not going to be able to work on this anymore. Partial y t partial x p. Yeah? Yeah? Yeah. Okay. And that is equal to to sum I equals 1 to n parentheses a TSR partial y t partial xp, which, by the way, is the sum of a sub t partial yt partial xp, t equals 1 to n, great, by adjunction of the n identities partial yi partial xp equal to partial Is this equation under equation 18 as disturbing to you as it is to me? Are those different typesetted things? Or does he really just mean that since those are equal, you can do something? All right, setting aside my many notational queries about the current set of equations, all right, setting aside these. What does Theorem 2 say? Theorem 2 says the system of differential equations 17 has the property that for some fixed integer p, it implies the set 18. Suppose it has the property that implies that for some fixed p. And suppose further that the matrices A sub I, in this case A sub t, right, are commutative. So Theorem 2 says, suppose 17 implies 18 for fixed p, and the A sub t, right, are what? Well, let's say A sub I. Fine, I'll use his lingo. A sub I equals to A, I, S, R are commutative. Then what? And what further? And the sum, I can start to see a trace here, right? He's got the dk I equals 1 to n. I mean, that looks like a trace of something, that being 0. Then there is a uniquely determined linear commutative associative algebra A over F, for which F is the generalized Cauchy-Riemann equations in the sense of the lemma. Oh, wait a minute. I'm an idiot. He said direct from the corollary of Theorem 2. I can't read. Sorry for wasting your time. Not entirely, though. I mean, probably you need to understand Theorem 2 to understand its corollary, right? What's the corollary to? It says it's a necessary and sufficient condition that the linearly independent equations, blah, determine an algebra A for which 20 is a set of generalized Cauchy-Riemann equations, is that. Oh, I see. This corollary is the n equals to 2 version of Theorem 2, actually. I see. N equals to 2 gives us corollary 2, which says just need, so we have for some ij, ji equals 1 to 2 of dk ij, partial yi, partial xj equals to 0. For that to be the generalized Cauchy-Riemann equations of an algebra, we just need that dk11 plus dk22 equal to 0. Since 21 holds, the coefficients of 20 may either be put into the form. Therefore, either A1 is I and commutative, or A2 is I and commutative. The corollary follows from Theorem 2. I had to think through that. Huh. guys have anything to add? What's that? I mean, the Jacobian, right? This is the Jacobian matrix. So if we fix k, right? If we fix k, yeah, if we fix this is exactly the trace. This is the trace of dk Jacobian of f. Yeah. Oh yeah, I'm sorry. Go on. We can stop. We can stop. I'm just. Yeah. Yeah, just for a second. That's the trace. You guys can go. It's cool. No, you're fine. So that's definitely the trace, right? So the BIs are the DK. You think so? Oh, so this I should, I mean, that's the thing. These are both traces. Both of these conditions are traces. So you're saying that you think this one is, well, this one's got to be that one, right? I mean, yeah. Oh, and you're saying that that is this. I think so. Anyway, so next time we meet, which I guess is next week, we'll pick up from here. Yeah, we had assessment day. Sorry, guys. Anyway,